Okay, chemical equilibrium. This is a cornerstone topic. This is something that we need to get a firm grasp on because it is used in every unit moving forward for the rest of the year. So, let's start off with a definition. Equilibrium is defined as the state when the forward reaction rate equals the reverse reaction rate. Right? So, reactions that are capable of equilibrium are often noted with a two-way arrow like that, double arrow. Sometimes the arrow is written this way, right? And sometimes the arrow is unequal in size, meaning sometimes the forward arrow is a little bit bigger than the reverse arrow. Sometimes the reverse arrow is bigger than the forward arrow. It kind of depends, and there's a reason why for that, which we'll talk about in just a bit. But the point is, you have some kind of arrow which goes both ways. Right? So equilibrium is a state, and when you are at chemical equilibrium, that is when the rates are equal. Right? So when equilibrium is achieved, what you need to understand is that the net concentration of the reactants and products do not change anymore. But the reaction still happens. If the reaction still happens, but the the net concentrations are no longer changing, that's where this term comes from. It's called dynamic equilibrium. It's like an equals ratio, even though changes are still happening. Right? So an example would be, in this classroom, if there's 20 people, in the next period, there will be 20 people, but they're not the same people. In the period after that, there's 20 people, but they're not the same people. People are constantly coming and going and coming and going, so there is change, right? But the number of people here is relatively constant, okay? So, real life example, let's say you have a water bottle. In a water bottle, you will have the same total amount of water as long as it's closed, right? So here's your water bottle, and you have some water. You didn't drink it all. There's going to be water vapor. The total amount of water is going to be the same regardless of if there's condensation taking place or not. So when there's lots of condensation, you're going to get all these water droplets clinging to the side of the bottle. But as long as the system remains closed, like as in nothing can come and go, right? No water leaves, no water enters. We have a dynamic equilibrium between the vaporization and the condensation. Right? Dynamic equilibrium in any one of those situations, as long as it's the same bottled water with the same mass. Okay, so anytime there's a gaseous equilibrium, it is assumed closed. Because if it wasn't assumed closed, then you'd be constantly losing the gas, which means you wouldn't have any material left. Okay, so let's talk about the equilibrium constants. You are familiar with kinetics rate constants. The equilibrium constant is related to that. It's based on it. So let's take this for example. Here we have the decomposition of dinitrogen tetroxide. Right? So our reactant ends up forming our product. Our product is nitrogen dioxide. If I asked you to simply write a rate law for this, you would take the reactant's concentration and whatever presumed rate it would be, and you'd write a differential rate law, just like this, just like you know. Now, if I wrote this reaction in reverse, but then I asked you to write a rate law for it, this is what you would write, because in the reverse direction, your reactant is relative to the direction. So our reactant in the reverse direction is NO2. And it's got a coefficient of 2, so that coefficient becomes the exponent. So by definition, because the forward rate and the reverse rate are equal, then these two rate laws can be set against each other. And rearranging to solve for the constant k then looks like this. I'm just going to divide both sides by N2O4, and I'm going to divide both sides by KR. And so this is how we arrive at this relationship. And because the value of k has not yet been defined, we would just redefine it in terms of a new variable kc. So kc then is ultimately set up as the ratio of the concentration of the product over the concentration of the reactant, with any coefficients becoming exponents. And this is the generic method for writing the equilibrium expression. And again, when I say equilibrium, I stress that this relationship only holds true when it is determined you are at equilibrium, when you're at the state of equilibrium. So another way to think of it is you can find what the value of this constant is if you know what the equilibrium concentrations are of the reactants and products. And that's like that is your first type of problem, is to be able to solve for the equilibrium constant. Okay. Generically, I should also mention that whenever you take, actually here it is, never mind. So generically, this setup is what we call the law of mass action. And the law of mass action is when you take the products or the reactants and set it equal to a constant, right? In this case, in any kind of reaction, note that your coefficients for any of these become the exponents. So obviously, if it's 1, then you don't need to write the exponent of 1. But if there is a coefficient other than 1, then yes, of course it must be written. All right, so that is how we take an equation and we set up the expression for the equilibrium constant. So we solve for this value, this equilibrium constant, k sub c. So just as an aside here, I want to mention, when you guys were sophomores, you learned about the equilibrium constant, but we called it KEQ. In AP, we're a little bit more specific because there's many types of Ks, as you will learn. And we're going to start off by using K sub C. The C stands for concentration. So in other words, KEQ is like a generic symbol. Kc is specific. There are many K values. There's KPs, there's KAs, there's KBs, there's KSPs, there's KFs. There's a lot of different Ks, and they all stand for different things. And we're going to go through them all, but right now we're starting with Kc, because it means that we're dealing with concentrations first. Okay. So we're able to set up this expression, and we're able to arrive at some kind of number as long as we have concentrations to plug in. But what does this number mean? What does this mean? Well, when the K value is larger than 1, that means that this reaction is product favored, which means once a state of equilibrium is achieved, there is more product than reactant. Which this should make sense because since K generically is products over reactants, then of course if the value is greater than 1, that means at equilibrium there's more product. So mathematically, that should make sense. If K is less than 1, the reaction is reactant favored. So that means reactants predominate. Okay, so magnitude of K, Kc, implies whether the reaction is what we call product favored or reactant favored. Okay? And in general, you're going to use the value 1 as the benchmark. Is it greater than 1? Is it less than 1? That's how you're going to decide. Okay. Another important idea in the concept of equilibrium is that equilibrium can be reached from either direction. And what that means is when you write a chemical reaction that is capable of equilibrium, equilibrium can be attained whether you start with reactants or whether you start with just products. So, for example, if we look at this equation here, did I have it? No, I don't have it here. So I'm going to rewrite an equation here. I'm going to write, so hydrogen plus nitrogen forms ammonia. Okay? And so the law of mass action for this would be written this way. Everybody take a second on that and agree that that makes sense to you? Okay? All right. So in this reaction, any reaction that is capable of equilibrium, it doesn't matter if you have reactants or if you have products. Equilibrium will be attained. All right? So in the first example, in the first graph here, notice how the concentration of hydrogen and the concentration of nitrogen is what we have an initial value of. And as this reaction progresses, the concentration of hydrogen is lowered, the concentration of nitrogen is lowered because as reactants they're being used up. Conversely, the concentration of the product starts at 0 but starts to increase slowly. And eventually what will happen is that the concentrations will all plateau. Once that plateau occurs, that's when you know that equilibrium is achieved. Once the concentrations are constant, now remember, the reactions are still happening, but they're happening in such proportions that the numbers no longer change. At the beginning, of course the numbers must change, because at the beginning we had no product. And the reaction continues, it plods along and plods along and plods along, and eventually you get to the point where the reaction, both forward and reverse reactions, are happening equally. Now let's look at the converse situation. In the second graph, we are starting with a concentration of the product NH3. So as this reaction begins, the concentration of the product decreases, decreases, decreases. All the while, the reactants start at 0, and those increase. And of course, like all reactions capable of equilibrium, eventually the concentrations will plateau for everything. And that is how you know when equilibrium is achieved. Now, a couple things that should be taken away from this. First, are the rates of change for the reactants in either graph the same? No. If I ask you to calculate the rate of change here and here, it's not the same, and that lends itself to the fact that stoichiometrically, your reaction rate of hydrogen is 3 times the reaction rate of nitrogen because of the coefficient, the mole ratios. The appearance of ammonia should be in magnitude twice the disappearance of nitrogen. Everybody follow? All right, so stoichiometrically affects the rates, okay? You knew this. Okay, so it doesn't matter whether you start with reactants or products, equilibrium will be attained. All right. Let's take a look at this next example here, the decomposition of hydrogen iodide. Right, so our reactants, our products. We are going to be, one of the most useful tools in solving equilibrium problems is what we call the ICE table. It stands for initial, change, and equilibrium. And so for virtually every problem, you're going to draw a little table here. Let me show an example of constructing the table. So here's my equation again. I'm rewriting it. You're going to draw yourself a little table underneath it. You should leave space for 3 rows. I, C, E. So in ICE tables, I should jot this down. In ICE tables, you should use only molarities or pressures. Okay? Don't use raw values like grams. Don't use moles. Okay? This is concentration dependent, so use molarities or use pressures. Now, in this case, we are given molar, and by default, right, far and away, the value that you'll use most of the time is molarity. But we will use pressures, and when we do use pressures, then we're solving for Kp, and you'll see why. All right, so in my ICE table here, just by inspecting what is told to us in the initial row, what they're telling us is at the beginning, we have a concentration of hydrogen iodide to start, 0.2, right? And if there is no hydrogen or iodine mentioned, then you are to assume that there is none. So there's nothing there. So what is found out then is once equilibrium was attained, these were the concentrations that were monitored. So you will then infer how much change occurred. For the hydrogen iodide, there was a decrease of 0.04. For the hydrogen and for the iodine, you have an increase of plus 0.02. How come the rate of change is not the same across the board? Why is hydrogen iodide different than hydrogen or iodine independently? Irina, what do you think?
Because there's 2 of it for every one of the 2 ices.
Yeah, because of the coefficient right here. You must pay attention to coefficients. If you ignore coefficients, you might as well not even do the ICE table because you're just not going to get right values. Okay? Coefficients matter. Coefficients. Pay attention to them. Okay. Hey, and guess what? One of the primary problems is to determine equilibrium values or determine the equilibrium constant. Guess what we can do now? We have the equilibrium concentrations. If you have the equilibrium concentrations, you can now solve for the equilibrium constant value because you need these. And we have those. What happened? Oh no, where am I? Here we are. Right? That's what we need to solve for the equilibrium constant, and we have each of those values, so we just substitute. The KQ will be whatever this turns out to be. About 0.0156. Now, the equilibrium constant, oddly, is unitless. It does not have a unit, unlike kinetics constants, where we take great pains to solve for the units. Oddly, I really can't tell you, and I've never found a satisfactory explanation as to why we don't bother with equilibrium constant units. We could pretty easily determine it. It would just be a matter of using molarities and canceling out and having powers, but no textbook that I've ever read, and I've never, maybe I could Google it, but they don't bother. Nobody in the chemistry field bothers with units on equilibrium constants. So, no constant, or no unit. Okay. All right, would you say that this reaction is product favored or reactant favored? It's reactant favored because that number is less than 1. If it's less than 1, that means there is more product at equilibrium than there is reactant. Okay? So that means it's a reaction that it doesn't happen very easily. It doesn't move forward very much. Okay? Let's look at another example here. So in experiment 2, we are starting with initial concentrations of the products, and we have no reactant initially. Yet, when we get to equilibrium, once it's achieved, and it would be achieved by this kind of change, we're subtracting the value of 0.02 on the right side. We are increasing by 0.16 on the left side, and we arrive at these equilibrium values. So, oh look, they happen to be the same as in experiment 1. The equilibrium constant will be the same. Which the equilibrium constant should be the same, right? Regardless of what your starting temperatures are, regardless of what your starting concentrations are, your equilibrium constant is unchanged. It might, vary by some small amount, but the point is it's generally going to be the same. And so I'm going to interject a rule here a little early, is that only temperatures can change equilibrium constant values.
Did you mean minus 0.08 for the change?
No. On the experiment 2?
Yeah, because 0.1 minus 0.02.
Oh, wait. Sorry. I did. Yes. Yes, thank you. Minus 0.08. That maybe that was an 8. That was kind of obscure. Kind of maybe it looked like a 2 to you, but in my mind it looked like an 8.
Okay.
Only temperature change can change, or only temperatures can change the equilibrium constant. Only temperatures, okay? You change concentrations, doesn't matter how much you change concentration by, the equilibrium constant will not change. But if you change the temperature, that will do it. All right? Experiment 3. What do we have going on in experiment 3? So, oh, look, we have initial concentrations for everything. 0.1 molar, 0.1 molar, 0.1 molar. Okay, well, it turns out that at equilibrium, we arrive at these concentrations of 0.24, 0.03, 0.03. So, if we were to, well, how did we get here? So this was minus 0.07, a minus 0.07, and a plus 0.14. I guess it doesn't really matter because we already have the equilibrium concentrations. But if we go ahead and plug this in, we're taking the products again, 0.03 squared over 0.24 quantity squared. Just to verify. Yep. Same value. All right, are you guys okay with that? Does not matter what your starting concentrations are, the equilibrium constant will be. Okay? Oh, here, I already mentioned that, but here it is again. Okay. So, your reactions won't all look the same. Sometimes you have what are called heterogeneous equilibria, and you know the word hetero means different. So it's an equilibrium reaction where you have different phases. All right, so we have gas, 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 but uh-oh, we got liquid. So whenever this happens, whenever you have a condensed state like solids and liquids, the condensed state does not have a measurable concentration. Because you cannot calculate the concentration for a solid or liquid, then you are to omit that species from the law of mass action. So when we write products of reactants, we are ignoring the water term here because it's a condensed state. So it mathematically cannot factor into our calculation. So we ignore it. And so this is how we would carry on calculating the Kc for this reaction. All right? Ignore solids, ignore liquids. You must use gases, you must use aqueous. because those are what we can find concentrations for. So what would the equilibrium expression look like for this reaction? What would I have for that one? What would that be? Angela, what would I get for that? Yeah, it would be Kc is equal to concentration of CO2. That's it. Now, initially, right, if initially, let's say you didn't pay attention to them, one might write this. Which, of course, would be incorrect. You cannot use those. All right? No big deal. Just ignore solids, ignore liquids. Okay, so we're going to get into some solving modes here, some problem-solving mode. So here we have a problem. And a lot of times equilibrium problems will preface with a temperature, and they will tell you at 100 degrees or at 200 degrees. And the reason why they're doing that is because the equilibrium constant is temperature dependent. You're not using the temperature number. It's just kind of like a reference. It's just kind of saying, like, you know, if there was a part B of a problem, they might say, well, now at 50 degrees, you know, find Kc, meaning that the Kc should be different if the temperature is different. But you're never going to use the temperature. All right, so don't be thrown off by that. Okay. So here we have a problem. They want to find Kc. In order to find Kc, you need equilibrium concentrations. In order to find equilibrium concentrations, you need an ice table. So rewrite the equation with an ice table underneath it. And oh look, they're giving you moles, and they're telling you the volume of the container. Why are they telling you the volume of the container? Because you need the molarity in an ice table, and you should only use molarities, right? So for N2O4 divided by 2 liters, that means your molarity, your initial molarity of N2O4 is actually 0.04. Okay. The NO2 is 0.24 divided by 2 liters is going to be 0.12 molar. Well, we don't need the M, it's implied. Okay. Oh, wait. I did a boo-boo. I didn't need an ice table for this because of these magic words. I put those numbers in the wrong place. Where should they be? They already gave me the equilibrium concentrations. Now, the purpose of an ice table is to find the equilibrium concentrations. If they give you the equilibrium concentrations, you actually didn't even need the ice table. So I did a little bit of extra work here, but it's okay. I figured it out, and this might happen. So Kc would be the concentration of NO2 at equilibrium squared over the concentration of N2O4 at equilibrium, which we have. So square that and solve. Point 0.36. So slightly reactant favored, right? Because it's under 1, not tremendously by a lot, but it's under 1. Okay. So what's the point of Kc? What is the point of equilibrium? Why are we here? Why is it so cold? Why are we wearing masks? All right. Kc, right? Here's what we can do with it. First, we need to determine the direction of the reaction. And sometimes we don't have enough information. So that brings about this new law of mass action called Q, right? Q is the original concentration quotient, whereas Kc is the equilibrium concentration quotient. Right? So if Kc is the ratio at equilibrium, Q is the ratio initially. That's how it differs. That means you can only use initial concentrations, hence the subscript. So, how do we decide, or what do we do with this value once we solve for Q? If we plug in initial concentrations, well, if Q is less than Kc, that means the system is going to make more product. It's going to move to the right. And the reason why it's doing that is because there's not enough product formed. Equilibrium is going to equilibrium, right? It's going to, reactants that are capable of equilibrium will get to equilibrium. And so if the current ratio of product to reactant is too low, you just got to wait. The reaction will get there. If the opposite is true, right? If the Q is larger than the Kc, what that means is that there's too much product. The reaction will break down product to increase the concentration of reactant. So we're going to have to do some evaluation. We're going to have to solve with initial concentrations. We're going to have to compare it to what the Kc is, and that will tell us the direction the reaction is going to proceed. Okay, so in this reaction here, I'm starting with initial concentrations of Hi to be 0.1, and there is no hydrogen, there's no iodine. Which direction is this reaction going to go? If there's no product, right? If there's no product, in order for equilibrium to be established, you need both reactants and products. So this reaction must go forward in order to get to an equilibrium. So if there's ever a zero for an initial, the reaction must go towards that direction and make that. Do you guys, maybe it's easier to see that in a nice table. All right, what this problem is starting out as is like this. Which way is this reaction going to proceed? It has to proceed to the right because there is no product. You must make some product. You must have a back and forth reaction. Well, currently there can be no reverse reaction if there's nothing on the right side to break down. Okay, so the plus and the minus for the changes would be indicated as such. Okay. What if we start with all three of them being 0.1 molar? So 2Hi forms H2 and I2. And we have initial concentrations of everything. Whoops, that's 1.0. Which direction is this going to go? And the reason why I'm asking which direction this is going to go, because in every ice table, I'm going to be adding and subtracting values. But I need to know which side it is that I subtract from and which side I add from. And that's the purpose of Q. So when I solve for Q, which is 1.0, everybody see why it's 1.0? Just write it out here to elucidate that. Right, products over reactants, okay? The value is 1. How does Q compare to Kc? Q is greater because remember Kc was earlier mentioned 0.016, right? Q is greater than 0.016. That means what? What's going to happen here? So yeah? It's going to go backwards. If Q is greater than K, there's too much product. So to alleviate that, you have to subtract from the product side and you have to add to the reactant side. And so I don't know what that value is. I don't know what the rate of change is yet. When I don't know, I just use a variable x, and that will be determined later. Coefficients matter still, right? So notice that here, the rate of addition for the reactant side is plus 2x because of coefficient of 2 on HI. All right, and you know what? Actually, since we're here, let's just finish the problem. And on a problem like this, the purpose would be to find what the concentrations at equilibrium are. And since the K is known, so the Kc would be concentration of H2 times concentration of I2 over the concentration of HI squared. And these, of course, are equilibrium values, so I can just substitute in everything that I know. 0.16 is equal to 1 minus x over 1 plus 2x quantity squared. Man, this is going to be a nasty polynomial. If only I had some kind of program specifically entered on my calculator that will allow this to be a pretty seamless operation. You guys have it so good these days. I did not have a solver when I was in high school. Remember to reset your x line to 0, and then it's alpha enter. All right, so I get a value of x to be we'll call it 0.70, which means my equilibrium values is going to be 0.3 molar, 0.3 molar, and 1.6. Did you guys get that? 0.7 for x? If not, once we get through, then I can go over the solver with you again here before you leave. Okay. Don't worry about it too much right now. Right now I want to focus on problem setup. Okay. So this next problem is a very similar problem. We have actually no, it's not. I'm sorry. We have initial concentration of HI only. Right? You're starting with this, and because you don't have any of the products, we know that we will be adding the values to the product side. Based on stoichiometry, we know that we're going to be subtracting the quantity of 2x. And so once we set up our law of mass action, because the Kc is known, we can, in this case here, we have a perfect square situation. So we don't even need the solver. We can just kind of math this out. Right, redistribute. I mean, but you can still use solver, of course, right? But you can simplify it before you enter in solver, either which way. We're able to find a value of x to be 0.02, and then we substitute back in, and then we're able to arrive at the concentrations. Okay. Do this one on your own. All right, I'm going to start writing this out. Did you guys get a value of x to be 0.06? Okay. So the nice thing about using a solver is that once your calculator registers what x is, you can just simply quit out of it, and then you can just type in like 0.1 minus x. I mean, you probably didn't need to in this situation, but when the number is a little messier, then it's helpful. So those are equilibrium concentrations. Ron.
Real quick, so it tells us that the reaction is reactant favored, right? So does NO2 have a higher concentration because of its stoichiometric coefficient? Mainly?
Yes.
Okay.
That, and I made up this number without consideration for the K and the actual concentration that I chose to start with, 0.1. But yes. So now 0.36, even though it's reactant favored, it's not that low of a number. As you will see, the K's can get really small, right? You can have K's with like powers of 10 to the exponents of like the negative 30s. Okay, so anything close to 1 is very close to equilibrium in and of itself. So we'll see extreme examples in just a bit here. Okay, so now we get to the part of the notes where there are sample equilibrium calculations, but I guess we've kind of been doing these all along anyways. But they're worth noting because there's sometimes problems are not going to be all ice tables. All right, sometimes they're going to involve a little more thought, and sometimes you can overthink it, and they're actually simpler than you think. So let's take a look at this reaction here. So here we are given, you know, the two reactants and products, and this is kind of a horrible choice of a reaction because there's so many C's and H's to write. And they're giving us the equilibrium constant. They're giving us yet the equilibrium the concentrations are for 3 of these, but they want to know the concentration of C2H5OH, of ethanol. They want to know the concentration of this guy, and you have everything else. Well, if you have everything else, but you're only missing one thing, this is just simply algebraic manipulation. All right, so you would write out your law of mass action. Really should change this for future notes. Oh, I guess it's not that bad. All right, so you write out your products over your reactants and note what it is that you are trying to find. You're trying to find the concentration of ethanol, and so you just kind of rearrange it. And I'm going to cheat. I'm just going to duplicate this and move stuff around. There we go. So we plug everything in. Let's see what you guys get. right, what's our ethanol concentration? Mm-hmm. Okay, so no ice table needed in this case. It's just manipulating the law of mass action, just moving it around. Okay. Another example. Phosphorus trichloride reacts with chlorine gas, PCl3 plus Cl2, to form phosphorus pentachloride, PCl5. A student places 0.2 moles of PCl3, 0.1 mole of Cl2 into a 1 liter flask. After the reaction came to equilibrium, it's found that the flask contains 0.12 molar PCl3. All right, so for that information, we can start filling in what we know in the ice table. So PCl3, 0.2 moles divided by 1 liter, well, that's 0.2 molar. Chlorine, 0.1 divided by 1, 0.1 molar. There was no PCl5 initially, so 0 there. At equilibrium, the concentration is 0.12 for PCl3. All right, so we need to finish and find the equilibrium values and what the Kc value is. So the first thing I can find is the PCl3 rate of change. Now, since I know how much PCl3 changes by, chlorine, I don't have any direct information about chlorine, but I do have indirect information. How do I find the concentration of chlorine? What could I use as a guide? Reed, what do you think? Can I find chlorine?
Shouldn't it be the same value as the change?
It should, and what is the reason why it's the same?
Because there's no coefficient since they both do that.
Yeah, they have the same coefficient of 1. Okay, so the rate of change is the same. If they have the same coefficient, they have the same rate of change. Okay, so 0.02 is my equilibrium concentration there. And applying that same sentiment then to the product, Kim, how do I find how much PCl5 is made? Either, Kim. What do you think? Use the force, and by force I mean mole ratios. Right. We just add the same amount. Because what's the mole ratio between chlorine and PCl5? What is it? It's 1 to 1. Plus 0.08. Obviously the sign is different. Okay, because it's on the other side. Right, we're making the product. All right, we have our equilibrium concentrations. The goal was to find Kc. $33 1/3. It's my favorite book series. Okay. How are we doing? This is a lot of equilibrium, right? It's kind of hard to stay balanced when we're doing so much equilibrating. So, let's see. Okay, I'm going to skip these two for now, and I'm going to assume that you can do those based on the examples that we have done. This is the last one I want to talk about for today. Sometimes you have an equilibrium constant that's just crazy, right? Look at this. 2.4 times 10 to the negative 17th. What in the world? Who's going to notice something, that small of a ratio? Okay. So let's work this problem, and then we'll talk about what to do with that constant. So we have an initial concentration of H2CO3. Let's write out our equation and our ice table. Aqueous. Sorry, I left these out. Okay. we have an initial concentration of 0.1 molar. There's nothing mentioned of the others. So we can use our mole ratios to determine our rates of change. What should my rates of change be? Based on what you see. I don't have a hard number, but I have to use an arbitrary value. Olivia, what do I do? When I don't know the value, but I need to put something there.
Oh, you put X's.
Let's use x's. So how many x's should I put for H2CO3?
1.
Just 1. Coefficient was 1. What about for H plus?
2.
And for CO3?
1.
Okay. All right. I have variables for my equilibrium concentrations. So now the next step is to write the law of mass action and substitute and solve. So Kc would be H plus squared times CO3 2 minus over H2CO3. And again, states matter. These are all aqueous and therefore they can all be used. Right? If one of these was a liquid or solid, it would have to be omitted. Okay, and now I substitute. The value of Kc was that crazy 2.4. 2.4 times 10 to the minus 17. And the concentration of H plus is 2x, quantity squared, times x over 0.1 minus x. Okay, so here's the thing. Plugging this into your solver, now your current computer calculators, your TI-84 pluses, probably could solve this. But this rule, but there's a workaround for this, and the reason why there's a workaround is because back in the day, this would be too difficult, too strenuous on the calculator, wouldn't be able to get to a solution. So rather than even go through that, let's just talk about it for a second. Do you see how this concentration right here, the 0.1 molar, 0.1 molar and the K value here, can you tell me how many orders of magnitude apart they are? How many orders of magnitude apart is your initial concentration and the equilibrium constant?
15, 16.
Yeah, 16 orders apart. Isn't that a big difference? So if we look at the size, the magnitude of this, and so remember what K values tell you, right? The smaller it is, then the less product favored this is, right? So whatever amount that x is going to be, when we subtract that value of x from 0.1 molar, how much is that going to change 0.1 molar? It's like saying, let's take 0.1 and from it, let's subtract 0.000000005. We can only round to 3 sig figs at most. So what is that number really going to be after the subtraction takes place? It's still going to be the same. This is called the simplification rule. And some textbooks call it the 1% rule. I actually kind of am more cautious than that, so here's what I'm going to tell you. When there is a 4 order of magnitude difference or greater, what you are going to do is you are going to ignore subtraction or addition of x to initial quantities. Huh? What does that mean? Well, look at our equilibrium concentrations, right? Where am I adding or subtracting x? Down here. So this is going to create a crazy solution, and the chance that your calculator gets it right is going to decrease the bigger this difference is. So rather than go down that rabbit hole, we are just going to rewrite the expression like this. The top we're going to leave alone because we're not adding or subtracting any value of x there. We are going to ignore, we are going to disregard the subtraction of x from within the quantity. And that makes this extremely simple to solve. Right? You're bypassing a whole half of that polynomial set. So now you don't even need the solver. You can just solve this straight up with just, math. Multiply both sides by 0.1. 4x cubed. Because 2x squared is going to be 4x squared times x is 4x cubed. So divide both sides by 4 and take the cubed root, and then you have x. X is 8.4 times 10 to the negative 7. And that is what's, now we're going to use that to determine the concentrations at equilibrium, because really that's pretty much always the goal. So for CO3, 2 minus 8.4 times 10 to the negative 7th molar. For H plus, it's going to be twice that. 1.7 times 10 to the minus 6th. And the reactant is still 0.1. I'm curious to see. I wonder if your calculator would still be able to solve this if we did not simplify. Yeah, Ron?
We got the same answer.
Did it really?
Yeah.
Okay. Well, when I started teaching, it struggled, and it would just kind of like dot error, and it wouldn't be able to get there. So, but in any event, it's a time saver. It's just it might have been able to solve this one. But that magnitude, that difference in orders increases. And the more it increases, the less likely your answer will be solved. Okay. I'm going to stop that here.